I am a protector, exploring the expanses of space to keep our planet safe, and all the species that call it home. I am a healer, giving doctors the vision to create amazing new cures. And using the heart's own magnetic field to diagnose itself. I am a guardian, searching a mountain of data to keep us safe when we travel. And a sea of people to find a lost child. I am a helper, powering autonomous machines that simplify our lives. Capture our greatest adventures. And make us whole again. I am a visionary, enabling taxis that don't need steering wheels. Those that don't need roads. I am even the composer of the music you're hearing. I am AI, brought to life by Nvidia, deep learning, and brilliant minds everywhere.
Ladies and gentlemen, please welcome Nvidia founder and CEO, Jensen Huang.
Hi, welcome to GTC, welcome to Santa Clara. GTC is the GPU Computing Developers Conference. We do it for you, for all of you whose work are simply impossible without a supercharged computer. Thousands of NVIDIA employees and our partners worked incredibly hard to pull GTC together for you. Let's give them a round of applause. Thank you, guys. I love you guys. Thank you. We have so much to talk about today. We have a lot of new products to show you. We're going to talk about amazing graphics. We're going to talk about amazing science, amazing AI, and amazing robots. We have so much to cover, so let's get going. Computer graphics is the driving force of the GPU. It is computationally insatiable. Recreating virtual reality is one of the most daunting computing tasks we know. And yet, on the other hand, it is an enormous industry. We want to visualize information, visualize experiences in all kinds of markets. As a result, the technology that we bring to bear and the size of the market combines into a gigantic R&D budget. It is the driving force of GPUs. Since 1979, when Turner Whitted wrote the paper on recursive ray tracing, in 1986, when Jim Kajia described the rendering equation, the computer graphics industry and computer scientists all over the world have been pursuing this holy grail, this dream of recreating photorealistic images. This is the way film is done. They trace rays through a scene as it strikes a surface, calculates the absorption, the reflection, the refraction, the luminescence, accumulates light from all the different sources and reflections and calculates the reflectance functions based on the materials that it strikes, accumulates all of that information, and generates a photorealistic image. Well, this is the way the film industry does it. And it takes thousands and thousands of CPUs and thousands of servers in order to calculate and compute each one of these frames. One CPU would take hours to compute one frame. And a movie has, as you know, hundreds of thousands of frames before they could create the final film. Well, when you look at this image, it is utterly beautiful. It's just super, super hard to produce. Well, the computer graphics engineers and architects at Nvidia isn't sitting still either. This is what modern computer graphics looks like. This is what a video game would look like. And in fact, it looks pretty amazing. The difference here is what I showed you earlier was generated one frame every many hours versus what's going on here with real-time rasterized computer graphics with programmable shading that we invented some 15 years ago, produces these images at 4K resolution at 60 frames per second. From one frame in many hours to 60 frames per second, that fundamental difference has been a gap we've been trying to close for literally 4 decades. Literally 4 decades. And in fact, it is incredibly hard. We look at this image today, and I can't tell you how proud I am. I mean, this is modern computer graphics. Look how incredible it looks. And yet, there are so many places we like to improve. For example, we use all kinds of special techniques to trick your eyes to see reflections, to see shadows. Ambient occlusion is where light accumulates on a surface, and because different surfaces are further away or occluded from the ambient light, it's darker. It's not a shadow, it just simply wasn't illuminated. Ambient occlusion. We use all kinds of tricks with our Z-buffer depth tricks to calculate in our programmable shaders to figure out which one of those pixels ought to be darker than the others. We use all kinds of tricks. Game developers will even render the scene completely in advance. And for all of the places where there's static lights, we will pre-bake the light. It's called light baking. But as a result, as you can see, so long as things don't move very much, the lighting conditions are relatively well reproduced. And it's quite beautiful. This is what ray-traced image would look like with global illumination. Notice those little details that bring a scene to life. The little details that bring a scene to life. So ray-traced global illumination, where light is simply emitted from everything that has a light source or is reflected. Diffused interreflection, where even objects that are matte in color could actually emit light as light reflects off of it. Global illumination. We use screen space reflection and environment maps. We render the environment and we create a cube map, which is then used as a texture in combination with our shader programs to recreate reflections. Or we could do it using ray tracing. Incredibly computationally intensive, but much, much more beautiful. We could do refractions as light travels through that glass. But as you guys know, refractions are hard to do, especially with a glass, because the glass has curved surfaces, and every time when you guys look at sun shining through a swimming pool, the curved surfaces accumulate a light volume that causes the refraction to look with these spines of shapes of light we call caustics. Notice it's very, very hard to do that here. In fact, it's not even visible here. We use all kinds of techniques to create the translucency of glass. And this is what it would look like if it was ray traced. It looks like crystal. And notice the beautiful caustics that are here. The beautiful caustics. Imagine if the light was moving. There are objects that absorb light. They absorb light, but they bounce inside and they re-emit the light. Subsurface scattering. Jade does that. Gummy bears do that. Car paint does that. Your skin does that. And that's why we don't look like a brown blob. That's why we look alive. Light goes through, picks up a little bit of shades of red, bounces around in your subdermis, and then reflects out. Makes you look alive. Subsurface scattering. We use all kinds of techniques to fake it today. Using ray tracing, the gummy bear looks like you could almost pick it up and eat it. Incredible. Incredible. And then here, we didn't show it here, but this gummy bear is actually being lit with the light from the caustics. All of those computationally intensive problems, the effects of light as it travels through your room, the environment, is so hard to compute. It is so hard to compute. And that's the reason why ray tracing has been so popular in film. And it is the holy grail, the dream for computer scientists for the last 40 years. It's incredible to see this when you look at it in motion. And so here's an example of it in motion. Let's take a look at this.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector.
If you ask me, who's ever in charge of this place should be transferred to Hoth. What? What?
You think she heard us?
Yeah, I think she heard us. At least we blend in for once.
Wow. Well, first of all, what you were looking at earlier was not a scene from the last Star Wars movie. In fact, it wasn't a scene in a movie at all. What you just saw was completely rendered in real time. Now let's show it to you. Okay, who's driving this morning? Steve, is that you?
Yep, we're here.
Okay, all right, this is
Got
Dr. Stephen Parker. He's been working on ray tracing his entire career. Since joining Nvidia 10 years ago, this has been the undertaking, this has been the endeavor of literally so many people in research, in software, in architecture, in hardware. Everybody's working together to make this possible. Now here, what he's going to show us now are some of the special effects that you can imagine, that you can do if you had ray tracing.
We've been working with Epic Games and ILM X Labs on a special project and are showing a prototype of RTX integrated into Unreal Engine 4 through Microsoft's DXR. In this case, we're showing area light shadows, which are quite important for cinematic visual effects. The tricky part is to get the contact hardening or the sharpening of the shadow near the base of the stormtroopers where they touch the ground. It's an important visual cue that helps us understand that those people are standing on the ground. And then we can also see them in a more complicated environment.
Now, Steve, the thing to say is when you say area lights is where light is being emitted from an area instead of a spot. Spotlights are relatively easy to do. Area lights are really hard to do. And the reason for that is it's essentially a whole bunch of spotlights. And so the way that the way that reflection works and the way that shadow works, shadows are so soft. And notice that there's so many different essentially the accumulation of a whole lot of shadows, and that's why they're so soft shadows.
Exactly. And in cinematics, it's important to control the shape and scale of the light so that you can control the shadows so that they fall where the producer would like them to fall. So,
that's incredible. Well, let's take a look at another scene.
Let's see
so
something
this is
shiny.
shadows and lighting. Now this is reflection.
So another thing that ray tracing is really good at is reflections. We can see them here in an environment such as the elevator that we saw in the clip. You can see the reflections on the stormtroopers as well as them reflecting each other. But to really show them off, we need to bring in something even more shiny. And so
now, look
here,
at this. This is reflections on reflections. Check out Captain Phasma's gun reflecting on Phasma's chest right there. You see that? Reflections of reflections.
so all those things have to be shaded multiple times, shading the primary surfaces as well as the reflections, and that's one of the things that makes it really difficult.
And these rays are bouncing all over this environment. These rays, every single one of those rays are bouncing off the environment, and every time it strikes a surface, it has to figure out, do I reflect, do I refract, am I absorbed, and how much is it absorbed? Where does other rays come from that I need to accumulate? And then it bounces off, and it goes to another place, and it strikes another surface. And then it strikes all these different surfaces. This light is bouncing all over the place as it strikes these surfaces, figures out what the rendering equation is at that moment as it strikes that surface, accumulates it for the entire scene with all of these billions and billions of rays. This is how this is recreated. Now, of course, doing so would just take an enormous number of computers. And that's why film studios have supercomputers. That's why Pixar has supercomputers. That's why Industrial Light and Magic has supercomputers. And they use these supercomputers to calculate these rays one at a time as it bounces and strikes these surfaces and creates this image. And the more reflections, the more refractions, the more ways that the ray can bounce before it's absorbed completely, the more reflections and refractions, the harder it is. There are so many little visual cues. Stephen Parker, Nvidia ray tracing team. What an amazing achievement. Ladies and gentlemen, everything that you're seeing here is completely in real time. Now, this complete demo, yep, there you go. It's completely in real time, and it's running on one DGX station. Instead of a supercomputer rendering these scenes one frame every 10 hours, this is now running on one DGX computer with 4 voltas in real time. This is what we can do now. $68,000 computer versus a supercomputer. That's great. Thank you, guys. So, ladies and gentlemen, we're announcing the Nvidia RTX technology. This has been 10 years in the making. You have seen us demonstrate pieces of it over time. But today, this is a very, very big deal. This is a very big deal because for the very first time, and by the way, I want to thank the team at ILM-X Labs and Epic and all of the engineers at NVIDIA that worked on this. This piece of work, the Star Wars rendering in real time, is really one of the first times that ray tracing has ever been done it is the first time that ray tracing has been done at this level in real time. So thank you very much, guys. Super proud of you guys. After 10 years, what makes this special is for the very first time, we can bring real-time ray tracing to the market. People can actually use it. The technology has been encapsulated into multiple layers, from our GPU architecture to the algorithms that makes it possible for us to do this. You are also seeing deep learning in action. Without deep learning, it would be impossible to have traced all of those rays. We use deep learning to essentially, whereas deep learning has been used in the past for super resolution, we're using them for super rays, predicting rays, so that we could fill in the spots that we know what the right answer is going to be using artificial intelligence. And so NVIDIA Volta GPU, the RTX technology, the solvers, the architectures, the libraries, has now been integrated into three of the most important rendering APIs. One, the Nvidia optics. Two, Microsoft's DX12 extension called DX Ray Tracing DXR. The work that we did with them is fantastic. And then now it's also going to be available in OpenGL Vulkan. We also are announcing today the world's largest GPU. The world's largest GPU. It's called the Quadro GV100. It is so large, we decided to paint it gold. Ladies and gentlemen, this is the Quadro GV100, the world's first workstation GPU based on the Volta architecture. It also is the first one that has a brand new interconnect between GPUs called NVLink 2, super high-speed interconnect between the two between two GPUs that basically extends the programming model, the memory model, out of our GPU into the other GPU, which means all of the memory reads and writes and all the atomics work exactly the same. Software doesn't have to change. The two GPUs connected through this new interconnect called NVLink is essentially one giant GPU. So these two GPUs working together, two GV100s, will become a revolutionary new workstation. It's going to be available from HP, Dell, and Lenovo. I think the announcement goes out today. It'll be available relatively soon. These two GPUs combined has 10,000 cores, 10,000 CUDA cores, 236 teraflops of tensor cores, all used to revolutionize modern computer graphics. The largest frame buffer in the world, 32 gigabytes of HBM2 per GPU, two of them together working completely unified inside an application of 64 gigabyte frame buffer HBM2. Ladies and gentlemen, the Quadro GV100 with the Nvidia RTX technology. Thank you, Paul. Creators and designers are going to love this. It is amazing how many frames are rendered each year. There are 400 games being made every single year. This is one of the largest industries in the world. And all of those beautiful lightings that you see is made possible by the technology, the technique that I described earlier called light baking. Basically using ray tracing to render the entire game in advance. And wherever there are static lights, bake it. Put it right into a light map. As a result, you get these wonderful crevices and shadows, and all of these details come out, and the whole world comes to life. The film industry uses this technology. Mowgli and Bagheera wouldn't be possible if it wasn't because of rendering technology. 500 movies made each year. Every single frame has been rendered multiple times during design, and then finally has to be done in final film. 10 hours on the highest performance GPU per frame. Just imagine how many CPUs per frame, how many CPUs are in those render farms. Product design. When you see advertisements and you see these commercials and these cars are driving around and they're being launched all over the world at the same time, the cars don't exist. They're all completely created using photorealistic rendering. Architecture design. There are no square buildings anymore. All the buildings in the world are beautiful, gigantic products. And the only way to imagine what it looks like inside, feels like inside, is to render it photorealistically. Architecture. We estimate 1 billion frames are rendered each year. With the Nvidia RTX technology and the Quadro GV100, I believe the number of frames that will be rendered will jump by a factor of 10, just so that you can iterate and try things before you get it done. You'll also get it done faster, but most importantly, you'll save money. As you know, everybody knows now, this is like common sense. The more GPUs you buy, the more money you save. That's right. The more GPUs you buy, the more money you save. This is now common sense. Now, let me illustrate it to you. This is what a render farm would look like. Look at this thing. It's incredible. 280 dual CPU servers. It consumes 168,000 watts. That's like 168 families in their homes being used to render images. This is before, this is after. This is with the Nvidia RTX technology, Quadro GV100. Look at this. 14 quad GPU servers, 24,000 watts. And you save millions of dollars. You save millions of dollars. This is what it looks like before. Probably a few $1 million. Call it 3, 4, 5. And this is what it looks like now. A few $100,000. Save millions of dollars. Come to GTC, learn how to save millions of dollars. Well, the industry is just so excited. We're so grateful for the adoption and the engagement and all the work that we're doing with the industry. From tools makers, Adobe, Autodesk, Dassault, engine makers, Epic, Unity, film studios, Pixar, Industrial Light, Magic, they've all come out to adopt this technology. The Nvidia RTX technology will completely revolutionize the way they do work. They could finally do ray tracing in real time. Try more frames, create more beautiful shots, deliver to the customer faster and on time, and more importantly, most importantly, save millions of dollars in the process. Incredible support from the industry. Gaming, design, film, architecture. This technology is the single most important advance in computer graphics in the last 15 years. And I say 15 years because programmable shaders that we invented has basically defined modern computer graphics. I believe Nvidia RTX is going to define the future of computer graphics. This is a very, very big deal. It's a very big market. Super, super proud of all the engineers that worked on it. Thanks a lot, guys. Good job. One of the best decisions we ever made was 15 years ago when we decided that a GPU, which was a graphics accelerator at the beginning, would become more and more general purpose. We wanted to become more and more general purpose because we felt that in order to create virtual reality, we had to simulate reality. We had to simulate light. We had to simulate physics. And that simulation has so many different algorithms, from particle physics and fluid dynamics, and of course, what you just saw earlier, ray tracing. The simulation of the physical world requires a general purpose supercomputing architecture. My kids told me this morning, Spencer and Madison told me this morning that this is our 10th year anniversary. The first year was called Envision. Since then, it was called GTC. This is our 10th year anniversary. We started GTC because we wanted to promote and to enable the industry to create applications on our GPUs. Because our GPUs are going to become more and more flexible. Over the years, we've advanced the architecture because accelerators tend to be very, very good at one thing. You accelerate one thing. Over the years, we've expanded the flexibility of our GPUs without sacrificing that one thing, which is accelerating computer graphics to its extreme, or accelerating whatever application. And of course, one of the applications you guys know very well about is our work on deep learning. Accelerating those applications to the speed of light, creating tools, creating systems, creating interconnect, evangelizing the programming model, all of you creating software and solvers on top of it, step by step by step, over the course of 10 years, and all of a sudden, one day, boom, the tipping point happened. It became a common sense computer architecture. It became a computer architecture that is available literally everywhere. And it couldn't have come at a better time and a more important time. At a time when all of these new applications are starting to show up. where AI software is writing software, but it needs a supercomputer to do it, where supercomputing is now the fundamental pillar of science, where people are starting to think about how do we create artificial intelligence autonomous machines that collaborate with us, that augment us. The timing couldn't be more perfect. Well, we're at the tipping point, and the number of people who are jumping on top of GPU computing is really growing and growing at an exponential rate. We're almost up to 1 million GPU developers, up 10 times in the last 5 years. The number of attendees of GTC, we are packed all the way to the end. We're packed all the way to the end, and we've got overflow, and Santa Clara is at its limit. Silicon Valley is at its limits. It has grown 4x in the 5 years. GTC is now a global event. The number of CUDA downloads has increased 5x in 5 years, but here's the amazing thing. 8 million downloads of CUDA, almost half of it was last year. 8 million downloads of CUDA, almost half of it was done last year, and remember, we started downloading it 10 years ago. The number of GPU flops in the top 50 supercomputers in the world has grown to 370 petaflops. We just announced our nation's 2 fastest supercomputers, Summit and Sierra, both GPU accelerated, each one of them about 100 petaflops. The fastest supercomputer in the United States was 20 petaflops, the Oak Ridge National Labs Titan. 370 petaflops is equivalent to three of the world's fastest supercomputers. 370 petaflops, an incredible amount. 15 times in 5 years. 15 times in 5 years. So clearly the adoption of GPU computing is growing, and it's growing at quite a fast rate. And we need larger computers. Even then, we need larger computers. The world needs larger computers because there's serious work to be done. There's serious groundbreaking science to be done. And there's so many examples of them. Whether it's reinventing the way we store energy, trying to understand the Earth core to predict future disasters, understanding and simulating weather, or just understanding how HIV viruses work. Each one of these simulations take days on the world's largest supercomputers. In the case of the work that is done at Caltech, 7 days on a Titan, 2 weeks on a Titan, 840 days, almost 3 years on the PIZ-DANT supercomputer. And of course, Blue Water, almost 2 weeks to simulate the HIV virus. Well, what's going to happen here is this. We're going to go build an exascale computer, and all of these simulation times will be compressed down to 1 day. But what's going to happen at the same time is that we're going to increase the simulation model by a factor of 100. And then we're back to 3 months. And then we'll go figure out a way to build a 10 exaflops computer. And we'll be able to reduce that simulation time. And then, of course, the size of science we'll be able to do will grow again. Science needs supercharged computers. And that's the reason why we're building supercharged computers. If you take a look at the last 5 years, there's no question now GPU-accelerated computing is the right answer. On the left, on this side, which is that? On the right is Fermi. This is our first GPU that you probably got to know about us, where the GPU computing universe learned about Nvidia. This is the GPU server circa 2013. This is the Volta server 5 years later, circa 2018. The amazing thing is running the simulations of these molecular dynamics codes, and there's so many of them, trying to simulate the human biology. The speed up that we created in the last 5 years is 25 times. Well, Moore's law is 10 times in 5 years. Moore's law, the miracle of laws, the law that has enabled just about every single industry and progress of science and the progress of society, was compounded over time 10x every 5 years. 10x every 5 years. Our GPUs have accelerated these molecular dynamic simulations 25x in the last 5 years. There's a new law going on. It's a supercharged law. There's a new law going on. And I think this is the future of computing. Well, the question is, how did that happen? Well, the way that it happened, of course, is it starts out with a highly specialized parallel processor. A highly specialized parallel processor we call the CUDA GPU. And of course, it is the largest and most complex semiconductor the world makes. But it's much, much more than that. The interconnect of these processors, the memory system of these processors, the way that it's architected into systems, all of the software on top of it. And I'm just showing you some of the stacks. Look at this. From cuBLAS, linear algebra, FFTs, random numbers, sparse linear algebra, the software stack in 2013 was 5.0. Amber 12.12, version 12. This is Amber 16. 9.0 across the board. Basically, we're continuously updating and continuously refining these algorithms and these solvers. We could design new architectures every single year. That's how we got from Kepler to Maxwell to Pascal to Volta. On top of it, we create new interconnects, NVLink. On top of that, we embrace new memory technologies and drive it to the speed of light. On top of that, we have new solvers and algorithms. On top of that, we work with system makers to create new systems. And on top of that, we work with all of the application developers to refactor, to optimize their software so that the entire algorithm could be highly accelerated. Now, the benefit to science is incredible. This is what a supercomputing rack looks like. It's much, much more densely populated because most supercomputers deliver a lot more power per rack. 20, 30,000 watts per rack. This is 600 dual CPU servers, 360,000 watts. And this is what it looks like if it was GPU accelerated. That's right. Work with me here. The more you buy, the more you save. That's right, work with me here. The more you buy, the more you save. This is not a complicated talk. Guys, this is not a complicated talk. First of all, I want to congratulate, speaking of talks, I want to congratulate John Hennessy and Dave Patterson for the recognition of the work that they've done, the Turing Awards. Hey guys, isn't it amazing? John, you're my hero. Speaking of talks, the guy gives just the most amazing computer architecture talks. This is not like one of them. This is much easier. There are only two messages I want to deliver today. One of them is, the more you buy, the more you save. Okay, all right, there'll be a quiz at the end. There's a second quiz coming up. Nvidia Tesla V100, big savings for HPC. One of the most important and one of the applications that I love the most of all of the work we do in HPC is the work that we do in revolutionizing modern medical imaging. Well, it turns out that early detection is the most powerful weapon against disease. The sooner you detect, the better. This is true for autonomous machines of all kinds. The sooner you detect, the better you detect, the better. Well, whether it's CT, computer tomography, magnetic resonance, ultrasound, mammography, which is low-dose X-rays, the positron emission, PET, each one of these modalities of medical imaging has been revolutionized recently using computational approaches. In fact, CUDA is embraced, and our GPUs are embraced throughout the medical imaging world for this very reason. Because it could take these sensors, these weak sensor information, do image processing on it, reconstruct the three-dimensional image, visualize it, segment it, detect things using deep learning. All of these techniques have now come together in medical imaging. On the left is a 15-year-old ultrasound image. In fact, it hasn't changed very much over the years. Most ultrasounds that you see in hospitals still look like that. On the right is a brand new medical imaging equipment from Philips Epic. It's unbelievable. It's unbelievable. It could do 3D reconstruction. It could visualize, it's as if there's a virtual light inside the womb. Look how beautiful it is. It does 3D segmentation, so it detects the baby and lifts it out of all the noise, and then it does beautiful rendering. And here you could tell they're using some amount of subsurface scattering so that the baby looks like there's the tone of flesh. Okay? Modern ultrasound. Well, this technology is used everywhere, as I mentioned. It's used in CT, MRIs, in PETs, in mammo, in ultrasound. And in addition to that, modern advances in deep learning and artificial intelligence is about to revolutionize the entire industry. We can now reconstruct images better than we could ever before. We could identify and segment brain tumor better than ever before. And we can visualize the images in a way that reveals a lot more insight using cinematic rendering than we ever could before. The entire stack of NVIDIA, from the GPU containers, the virtualized GPUs, CUDA, cuDNN, RTX, OpenGL, all of the solvers and all the libraries integrated into these imaging applications. That entire stack is identical to everything that I've talked to you about. It's identical to everything I've already talked about. Well, the unfortunate thing is this. There's some 3, 4, 5 million medical instruments that are installed all over hospitals all over the world. So let's call it 3 million instruments. 100,000 new ones are being sold each year, which basically says it's going to take about 30 years before we can replace the installed base. And so the question is, how do we solve this problem? We can't wait for 30 years. Can we take advantage of the same basic techniques that we've now seen in modern computing, where you have connected devices connected to data centers, and those data centers essentially have supercomputers that are virtualized? We have an initiative, a project in our company we called Project Clara. Clara, in short, is a medical imaging supercomputer. But what it is a data center, virtualized, remoted, multimodality, multi-user computational medical instrument. Well, that is such a long description of what it is, we decided to call it's a medical imaging supercomputer. You could put it in the data center, you can put it in the cloud, and because of the technology we've already talked to you about, it's possible for us to actually virtually upgrade every single medical instrument. Let me show it to you. Fausto.
Hey.
Fausto, hey, man.
So what we are seeing here is
Wait.
Oh, sorry.
Yeah, LUA, buddy. Forget it. Inside joke. I want to prepare his language so that you understand it. No. This is one of our scientists in our company, and this is his field of expertise. This is where he dedicates his life. Dr. Fausto.
Dr. Jensen.
That's right. Every time I call him doctor, he calls me doctor. And another inside joke. Hey, with your friends in the company, you got a lot of inside jokes. And so Dr. Fausto has been working on medical imaging for some time. And so what he's about to show you is something that's really amazing. Go ahead, tell us.
So sure. So what you are seeing here is a beating human heart, and this is an echocardiogram. Actually, we are seeing the left ventricle of the heart, which is pumping blood. And basically, this is the type of image that a doctor would look at when he diagnoses your heart functionality. And yeah, so this is 2D, but our body, of course, is 3D. So there is more information from the scan that we can acquire. So when we switch to 3D, we see a more complete picture like this.
And so this basically is a scan. It's an traditional ultrasound scan coming off of a 15-year-old instrument that we then take into this computational medical imaging supercomputer, this MIS, and this is what comes out of it. Does that make sense? Okay, you take this ultrasound machine that's sitting in a hospital, it's already on the network anyways, you stream the ultrasound information into your data center, and your data center running this stack on top of a GPU server creates this miracle on the right. And now it's volumetric. Keep going.
Yes.
That's nothing. Wait.
Okay, so,
Get so excited.
at this point, we see that we barely see basically the chambers here, and we can analyze more of the motion of the left ventricle by using deep learning. And we resort to use a state-of-the-art deep learning method. It's a fully convolutional neural network in 3D called VNet. We revisited it. We used the unprecedented resolution of 256 cubic voxel, which is 16 million values per scan, per frame. And we have asked deep learning to interpret it for us. And now we can see the chambers moving across the cardiac cycle, the left ventricle moving across the cardiac cycle, and segmented very well.
Now, just think, you got to realize what's happening. There's an artificial intelligence network here that is running on the original black and white gray scan that you saw. And from that scan, from that ultrasound scan, it inferred what this left ventricle, where the left ventricle is. It segmented it out. It segmented it out in motion, and it segmented it out in 3D. Guys, if that's not amazing, that's pretty incredible. That's pretty incredible. Keep faster. That's amazing work, man. Go.
Of course, there is more even to this story. So now we can get values. We can get very precise explanation of what we are seeing, and markers that tell us how well the heart is functioning. We can get the ejection fraction, the volume of the chamber of end systolic and diastolic moments, and the amount of blood that is ejected with each heartbeat. And we can just augment the view of the doctor in this way, in an almost transparent way, where the 2D view is augmented with the 3D information.
That's cool. Fausto, thank you. Your ejection volume was running about 80%.
At this moment, yes.
You think so? Maybe 99%, everything coming in was going out. That's fantastic. And so here's what we're going to do. We're going to create this server with this stack, this virtualized stack on top, and it's going to be remoted into all of these medical instruments all over the hospital. And then you'll be able to scan using your current installed base of scanners, and then we'll post-process it using AI to infer more information from it. We could also use all kinds of new computational techniques to improve the image and to visualize that image. We call this the medical imaging supercomputer. It's so great. We have partners all over the world working with us, and there's, this is an area that we've been working with and working on for quite some time. And so NVIDIA's new Project Clara, this brand new platform of ours, we're getting a lot of advice and developing and working with startups and research hospitals and healthcare providers in all the different modalities. Okay? Ladies and gentlemen, Clara. Deep learning has completely turbocharged modern AI. This incredible algorithm that can automatically detect the important features, out of data. And from this algorithm, it could construct hierarchically knowledge representations. And these knowledge representations, if you give it enough information, if enough data, it would become more and more robust and recognize a larger diversity of that space, become more intelligent. Deep learning has revolutionized modern AI. The thing that deep learning needs, though, is a ton of data, and more importantly, a ton of compute. And the reason for that is it just iteratively goes through and tries to figure out what are the important features using all of these incredibly revolutionary algorithms. Our strategy at NVIDIA is to advance GPU computing for deep learning, for AI, at the speed of light. from the processor development to the systems, the interconnects, the way we construct systems, to all of the software layers that are on top of it, making it available and partnering with cloud service providers and OEMs everywhere. Irrespective of what AI framework you use or what AI network you're trying to create, wherever you are, we will support it. And we will support it from end to end, so that the frameworks that you use to develop the networks and models will be deployable in large scale. And we would even make it possible for you to access our platform in every possible way and in any sort of way. Whether you would like to build a personal supercomputer for a few $1,000s with our Titan V, or to be able to rent time in the cloud for a few dollars an hour, or to be able to build your own supercomputing cluster, or just to buy one from us. We're going to make it possible for you to do your work at the speed of light and to be able to do it anywhere. Today, we're announcing several big things. First, we are doubling our GPU. The Volta V100 is now 32 gigabytes of HBM2 memory. It's twice the size of what it used to be. Now, this is so important, and the reason for that, and I'll show you later, the networks are getting larger and larger and larger. And so it doesn't fit in 16 gigabytes. Researchers would like to not worry about memory size while they're developing their neural networks, and 32 gigabytes gives them just a lot more space. HBM2, the fastest memory in the world, connected to the Volta V100. It'll be available as of now, and the next DGX as you buy, it'll be available in the cloud very, very shortly. It is in complete volume production everywhere. The new Volta with 32 gig. Neural networks are growing and evolving at an extraordinary rate, at a lightning rate. What started out just 5 years ago with the AlexNet, Alex Krizhevsky's now world-famous AlexNet, was 8 layers deep, had millions of parameters. 8 layers deep, millions of parameters. 8 layers deep and millions of parameters. It's a CNN. The CNN was first developed and produced or created by Yann LeCun, and the training technique is called stochastic gradient descent by Jeff Hinton. And it was implemented in AlexNet for the very first time, and it won the ImageNet competition. Well, 5 short years later, thousands of species have emerged. Thousands of species of artificial intelligence networks, models of all different types, from the CNNs of Yann LeCun to the RNNs that was first done at Schmidhuber's lab in Switzerland, the generative adversarial networks of Ian Goodfellow, deep reinforcement learning that was most recently done by DeepMind, Demis's DeepMind, and Peter Beal over at Berkeley. All of these different architectures have hundreds of different implementations. The number of species is growing so incredibly, and there are so many new ones coming out. Hinton just recently disclosed the capsule net so that it could not only recognize images in its image form, but to learn the geometric form of the images. So many new techniques. Neural collaborative filtering, NCF, which is used for recommenders. What started out just 5 years ago as 8 layers and a few million parameters is now hundreds of layers and billions of parameters. 8 layers and millions of parameters to hundreds of layers, billions of parameters. Neural network models have increased in complexity, not to mention the number of species, the thousands of species that are now out there. Neural network models have now grown in complexity 500 times in just 5 years. 500 times in 5 years. Remember, Moore's Law would have only kept up with 10x of that. 500 times in 5 years. So the world wants, the researchers all over the world wants, just a gigantic GPU. Not a big one. A gigantic one. Not a huge one. A gigantic one. And so, ladies and gentlemen, today, I would like to announce the world's largest GPUs. This is the world's largest GPU. This is 16 Volta equivalents connected by 12 brand new high throughput switches that the world has never seen. It's called NV switch. These 16 Tesla V100 equivalents, each with 32 gigabytes, creates virtually a 512 gigabyte memory. Not only that, these 512 gigabyte memories, the way you address the memory and the way that every single GPU could talk to the memory of another GPU, completely using the same memory model. The memory fabric semantic on our chip that connects all of the processors have been extended out of this chip, out of the GPU, onto the NV switches, connecting each and every one of them. In total, 14 terabytes per second of aggregate bandwidth. 14 terabytes. So that's, what is that? Let's think about that. 14,000 gigabytes. And let's say if a high-resolution movie is 10 gigabytes. Okay? So 14,000 gigabytes, 1,440 movies. 1,440 movies. More movies than any human has ever seen could be transferred across this switch in 1 second, like that. Ladies and gentlemen, 14,000 movies. $14,000 movies downloaded in 1 second. Dream come true. Altogether, 81,900 CUDA cores, 2 petaflops. This GPU is 2 petaflops. I told you earlier, the fastest supercomputer on the planet is 125. The fastest supercomputer in America is 100 petaflops. This is 2 petaflops of tensor cores for AI on this GPU, the world's largest GPU. Let me show it to you. No, that thing. Hang on a second. You know, guys, here's the thing. We're so busy pulling this stuff together, we don't rehearse. Okay, our rehearsal is basically grip it and rip it. Ladies and gentlemen, the world's largest GPU. You didn't fall for that, did you? You didn't fall for that. Hang on a second. This isn't the world's largest GPU. This is the world's largest GPU. Guys, it's sitting in plain sight, hiding in plain sight right here. Sandy, if I could give that to you. Now, I understood earlier that was that the game plan for me to do this myself? Oh, okay, it wasn't? All right. Ladies and gentlemen, grip it and rip it. This, ladies and gentlemen, is the world's largest GPU. Now, what you're looking at is something that's really, truly amazing. So let me show it to you this way, and I'll come back to that. Okay? This switch has 2 billion transistors made of TSMC's 12 nanometer FinFET. This, great process. Every one of these switches, and there are 12 of them, every one of these switches has 18 links, which are 8 bits wide, 18 NV links, 8 bits wide, with a SerDes that's moving at 25 gigabits per second. 25 gigabits per second on just one signal. There's 8 of them per link. There's 18 links on this one chip, and it's bidirectional. Altogether, It creates 7.2 terabits per second, or 900 gigabytes per second. So 900 gigabytes per second, by the way, of bandwidth, well, that's a lot of movies too. So 7.2 terabits per second, 900 gigabytes per second, goes through one switch. There are 12 switches. 12 switches. What that basically says is that every single GPU can communicate to every other single GPU at 20 times the bandwidth of PCI Express. Isn't that amazing? Every single GPU can talk to every other GPU. And every single GPU can talk to every single GPU in a non-blocking way. It's a fabric. It's not a network, it's a switch. It's a non-blocking fabric switch with a memory semantics, memory programming model that's exactly the same as what's inside our chip. And therefore, all the reads and all the writes and all the atomics just works across this. The bandwidth and the performance and the latency of this switch is incredibly low. It's incredibly low. Unlike a network, this is a switch, which means every single GPU can talk to the other GPUs with extremely low latency. You want to read, you want to synchronize a parameter, it takes no time. 300 gigabytes per second. And altogether, NVIDIA's largest graphics card. This is what it looks like. The largest graphics card. The largest graphics card the world has ever made. The largest graphics card the world's ever, 2 petaflops, 512 gigabytes. Most graphics cards in the world today, 2 or 3 gigabytes. 2 or 3 gigabytes. This is 512 gigabytes. 10,000 watts. 10,000 watts only. Only 10,000 watts. Only 10,000 watts. The amount of airflow is really quite amazing to cool it. And we designed this porous fabric in air intake in the front. It looks beautiful, but it's incredibly functional. Air comes traveling through it, flows through all of our chips. 10,000 watts of energy power is being thermal managed. 350 pounds. No human could lift it. No, 350 pounds. The first time I saw that, I was thinking, I could lift that. Didn't move. And I'm fairly strong, upper body strength. And so, 350 pounds. What's inside it is 16 Tesla V132 gigs with 12 NV switches. And it's got this incredible what's called a playing card. It basically has 200 times. It has 200 times the bandwidth of the highest speed NIC on the planet. So imagine it's like 200 NICs of connecting the top to the bottom, connecting the top GPU tray to the bottom GPU tray. Each NIC, call it $1,000, $2,000. Call it $1,000. $200,000 of NICs would be required to connect the top to the bottom. It has that much bandwidth. It has that much bandwidth. If we were to use networking cards, well, we still have to connect multiple of these, and so we have 8 of the world's highest speed NICs from Mellanox to connect multiple of these systems together. It has the two fastest CPUs we can possibly buy, the Xeon Platinums. 30 terabytes of storage. 30 terabytes of storage on the system, because as you know, we're going to crunch through a lot of data really, really fast. So all together, ladies and gentlemen, it looks like this. This is the Nvidia DGX2, the world's largest GPU, the world's largest add-in card, 2 petaflops, 512 gigabytes, 350 pounds, and just beautiful. This is... This is what an engineer finds beautiful, you guys. This is sexy. This is beautiful. This is unbelievable, incredibly beautiful. And not to, guys, did you guys notice the animation? NVIDIA's artists are so spectacular. This entire animation was shot with 112 shots. It's photographed, it's stop motion animation. This is not 3D. You know that we could do it in 3D, but we chose not to. Why? Because it's more fun. You guys want to see it again? Oh, stop motion animation, guys. Check it out. Guys, I love you guys. It's incredible. Tim Burton, you got nothing on us. Look at that. The world's largest GPU, 350 pounds. Well, let's see what it can do. 10 times faster than DGX-1. Does that even make any sense? 10 times faster than DGX-1. And so this is 6 months ago. This is literally 6 months ago. We showed these numbers. And the entire stack, look at the entire stack. There's so much software that's necessary to build this. This is a high-performance computer. It's a supercomputer designed for deep learning. And so look at this entire stack of software that was optimized. As a result, running PyTorch, the framework, and training FairSeq, the sequence-to-sequence model used for natural language, used for machine translation, literally took 15 days on a DGX-1, which was a world record at the time, and now it takes 1.5 days. Well, the amazing thing is, the researchers don't have 13 days left to sit around. The researchers are now using all kinds of techniques to use AI to create AIs. And so the number of experiments, the number of permutations, the exploration space of AI, sweeping through all the different configurations of architectures and the way to compose it, the number of layers, the training rates, sweeping through all of those hyperparameters and sweeping through all the different architectures at the same time is going to create just hundreds of experiments at one time. And so as a result, with bigger networks, more data, more experimentation, DGX-2 couldn't have come at a better time. And so it is 10 times in 6 months. Now, the thing that's really amazing is this. How much should we charge? I mean, look, it took hundreds of millions of dollars of engineering. It took hundreds of millions of dollars of engineering. This is the first unit, so this is, call it $250 million. And for just an incredible friend-to-friend price of $1.5 million, it seems like it doesn't even seem fair. It doesn't seem fair at all. Nah. Ladies and gentlemen, $399,000. You guys understand there are only two themes in this conference. That's right. The more you buy, the more you save. Okay? This front row's got it. We're going to keep working. All right? The more you buy, the more you save. And so $399,000 for the world's most advanced, most powerful computer. This is what it replaces. 300 dual CPU servers easily for $3 million. Easily for $3 million. Easily for $3 million. But the important thing is 180,000 watts, 180 watts, in order to train FairSeq in 1.5 days. Well, it only takes one of these beautiful DGX-2, just one DGX-2, 10,000 watts, only 10,000 watts. 1/18 the power, 1/8 the cost. The more you buy, the more you save. It's incredible. You know, it's truly amazing how far we've come in just the last 5 years. We started talking about deep learning about 6 or 7 years ago, and at the time, the effectiveness wasn't anywhere near what it is today. 5 years later, since AlexNet, The progress that we've made is literally incredible. And I think it'd just be kind of fun just to do a report card, see what happened in the last 5 years. This is what it looks like. This is what Alex Krzyzewski trained AlexNet on. Two GTX 580s. Two GTX 580s. And it took him 6 days. But those were 6 worthwhile days because he became world famous, he won ImageNet, and kicked off the deep learning revolution. 5 years later, we could train it in 18 minutes. 5 years later, we could train it in 18 minutes, 500 times faster. 500 times faster. Isn't that amazing, guys? To be able to do a task 500 times faster in 5 years. To be able to do any task 500 times faster. Any task of great importance 500 times faster. Or to be able to do a task of great importance 500 times larger in the same time. This is some kind of a supercharged law that we're experiencing. Well, one of the things that made it possible, of course, is what I said earlier. This is an innovation that is not just about a chip. This is an innovation about the entire stack. Everything was touched. Thousands of engineers all over our company, from VLSI to process engineering to package engineering to circuit design, to architecture to chip design, system software, solvers and libraries and algorithms and systems, all got involved. This is the effort. This is the work. This is the body of work of literally every single employee at NVIDIA. We are all in on deep learning, and this is the result. And so over the next several years, it's going to be just utterly incredible because we're just picking up steam. This is some new type of computing. The amount of data is growing exponentially. There's evidence that with GPU computing, the computation is growing exponentially. And as a result, deep learning networks and deep learning models, AI models, are growing in capability and effectiveness at a double exponential. At a double exponential. More data, more computing, both on an exponential growth, compounding together into some kind of a double exponential for AI. That's one of the reasons why it's moving so fast. Really, really exciting times. The system is complicated, and the software is complicated. And so what we've done is we've created containers to containerize all of these complicated softwares that are optimized into one container at a time. We put them into Tupperwares, if you will. And by putting them into these Tupperwares, we put them up in the cloud. We call it the NGC, the NVIDIA GPU Cloud. The NVIDIA GPU Cloud is not cloud computing. NVIDIA GPU Cloud is a cloud registry of all of these containers. 20,000 organizations have downloaded our containers. It's running in clouds. It's running in data centers. It's running all over the place. These NGC containers are just completely fabulous. And the reason for that is because irrespective of what cloud you run on, it's exactly the same stack. Because all the clouds have NVIDIA GPUs. All of the clouds now can run these stacks. All you have to do is come to that registry. You log in, you download, you run. You log in, you download, you run. It's about like that. 1, 2, 3, easy peasy. 20,000 registered users or organizations, a lot more users, 30 containers. Last year when I stood here, there were a handful. We've updated them, improved them, enhanced them, and we added a whole bunch more to them. And NGC has now been certified. We've certified. We have to test each and every one of these architectures on the data centers that we run on. We've certified AWS, and just today, we're announcing that Google Cloud Platform, GCP, Ali Cloud, Oracle Cloud will also be certified, has also been certified. Okay, so now they're available on multiple clouds. This is the only architecture that is any cloud. And in fact, it also runs obviously on DGXs, so it runs on any cloud and in-prem, so that's hybrid cloud. So ladies and gentlemen, our latest release of NGC. Plaster. Programmability, because the number of network species is growing exponentially. And they're evolving, they're getting more and more complicated. Latency, because without low latency, you can't have a good quality of service. Accuracy. If your model isn't accurate, there is no way that it could predict the right answer, or more importantly, revenues get hurt. Quality of service is compromised. Prediction is compromised. Size. The smaller these networks are, the more of these services we can fit in a data center. Throughput. Ultimately, these data centers are enormous capital investments, and the higher the throughput for the billions of people who are using it, the lower the cost, the more money you save. Energy efficiency. We are consuming a lot of energy all around the world. We need a computing model that dramatically reduces energy. Energy efficiency and rate of learning. Rate of learning. In machine learning, it's about the amount of data that you have, the amount of computing you have, but ultimately it's about how fast you're learning. The more new data you have, the faster computers you have, the faster rate of learning. You're going to deploy the model. You're going to learn from the new experiences. You're going to collect new data. You're going to train the current model. You're going to deploy it. That rate of learning is what defines success in the new world of machine learning. Ladies and gentlemen, I invented this word. Plaster. The second thing I want you to remember today, this is not a complicated conference. More you buy, the more you save. And number two, inference is complicated. Anybody who thinks that inference is easy, you know what, I'm just going to go buy a ASIC, stick it in my data center. Here's an ASIC, here's an FPGA, I'm going to stick that in my data center. Unfortunately, we know that hyperscale data centers are the most complicated computers the world has ever made. It's the size of these rooms. Billions of dollars are dedicated to it. It serves billions of people. How could it be simple? Building one computer for one user is plenty hard enough as it is. Building a supercomputer, hyperscale, that serves billions of people, delivering great quality of service while minimizing operational cost, it can't possibly be easy. Inference is hard because everything matters. Programmability matters, latency matters, accuracy matters, size matters, throughput matters, energy efficiency matters, and rate of learning matters. God, how did I do that? Come on, you guys, that's fairly good. I was trying to figure out how I was going to explain the complexity of inference last night. This is it. Brand new slide. Just one slide. We're done. Plaster. So we've dedicated just an enormous amount of resources to solving this problem for inference for hyperscale data centers. Their workload is really complicated. From image and video workload, natural language understanding workload, recommendation systems, recommenders, speech synthesis, speech recognition. They have all kinds of different types of networks. Sequence-to-sequence networks, deep generator networks, something perceptron. What's MLP? Where's Mike Houston? Multi-layer perceptrons, for God's sakes. Neural collaboration filters. Okay, recurrent neural networks, CNNs, of course. And so we started working on TensorRT, which takes the output of these frameworks, which are these massively complex computational graphs, and we have to target for all of the parameters that I just told you about. And we got to make that network as small as possible, as high performance as possible, and yet retain all of its accuracy. And each one of the target devices, of course, are a little different because our GPUs for deployment are different than the GPUs for training. And so initially, 1 year ago, we announced CNN. And then 6 months later, we announced 8-bit integer so that we could have multiple types of precision so that we could adapt for which one of the networks could lose a little precision at the benefit of a lot more throughput. We then supported Tensor Core 6 months ago. Today, we're announcing the largest battery of new tools, the largest battery of new algorithms and new libraries for inference that we've ever announced. First of all, TensorRT 4.0. Brand new TensorRT. It now has the ability to handle recurrent neural networks, sequence to sequence. It has deep integration into TensorFlow. I want to thank the engineers at Google who took TensorRT and our compilers and integrated it natively into TensorFlow. And so in the future, when you're done training the network, you could run that network fully optimized right on the target device. We worked with the team of Caldi Framework, the most popular voice recognition, speech recognition framework called Caldi, has now been fully optimized for TensorRT, for NVIDIA's architecture. And then lastly, Onyx, a brand new backend that supports PyTorch, supports MXNet, supports Windows, and has the same backend for Windows ML. We now have full optimization across the stack, and as a result, the trained networks that we train in all these different types of networks and all these different types of frameworks can now have the opportunity to be deployed into the world's hyperscale data centers. Four brand new capabilities addressing literally the entire stack of the workloads. Still lots and lots of work that we have to do in collaborating with all of you in your hyperscale data centers. But if we're successful in doing so, the millions of hyperscale servers can now be accelerated. Up until now, we've only been able to accelerate just those ones that are really focused on image and video. But in the future, starting with this generation, starting with today, we can now accelerate voice, speech, natural language understanding, recommender systems, as well as images and videos. Well, we've pulled together some of the latest results. It's really, truly amazing. Images are accelerated 190 times. Natural language, this is the Google Natural Machine Translator, GNMT for natural language understanding, 50 times. The neural collaborative filter that is in the SAP recommendation system that IBM recently announced as well, those architectures, NCF has been accelerated 45 times. Speech synthesis, WaveNet, 36 times, and speech recognition, 60 times. If we just assume that video and images and speech and voice and all of that stuff is all on balance approximately equal load, in aggregate, we're going to speed up hyperscale data centers with our GPUs with this generation of optimizations 100x. We would increase the throughput by 100x. Or another way of saying it is we're going to save a lot of money. You guys, come on, we've done this before. You guys know the drill. The more you buy, the more you save. And with 100x speed up, just imagine how much you will save. Well, now that we have all these accelerated frameworks and all these accelerated code, how do we deploy it into the world's data centers? Well, it turns out there's this thing called Kubernetes. Ladies and gentlemen, today, yeah, it's okay. I know. Kubernetes on Nvidia GPUs. Kubernetes on Nvidia GPUs. Kubernetes on Nvidia GPUs is going to bring so much joy. So much joy. There are people watching this out on the web going, that guy's lost it. That brings joy? Wow. Yes, this is going to bring joy. And this is going to bring joy because Kubernetes is allows us to take these massive workloads that are servicing billions of people, and it's an orchestration layer that orchestrates the workload that's coming in from the cloud and orchestrated across the resources of the hyperscale data center. Lots of CPUs and lots of memories, lots of networking, lots of storage, and it needs to orchestrate it across the sea of servers. And today, it is GPU aware, and it's GPU accelerated. So Kubernetes is now GPU aware. The Docker container is now GPU accelerated. You've got all of the frameworks that I talked about, which is GPU accelerated. And now you got all these inferencing workloads that are now GPU accelerated. And you've got NVIDIA GPUs in all these clouds, and NVIDIA GPUs in all these data centers and servers. And you've got this incredible, wonderful orchestration layer system software called Kubernetes. Life is complete. Okay, let me show it to you. Guys, Justin. This is Justin. Justin is, of course, you guys have seen this flowers before. Now, we're going to do the flowers a little bit differently today. So this is flowers, of course, running on CPUs, four images per second, and the fastest Skylake that we have. And so, Justin, take it away, sir.
Yeah, absolutely.
Oh, Ryan, excuse me. I'm sorry. Is Ryan?
Yeah,
Justin's
I was wondering
coming
if
up.
we're going to switch it up, but Justin
You guys got
nervous.
I'm sorry. No, it's not me.
Absolutely. So as you said, like TensorRT and inference performance, we've laid out the value for it right here. So this is the miracle of deep learning, showing flowers using ResNet 152 on Intel's latest Skylake CPU. So if we click on these, we can see these flowers.
Pelargonium. That's a Snapdragon. Hey, guys. Wow. Come on. That's industry stuff. People in the tech industry, we should go, you recognize, I didn't know that it was a flower. It's awesome. Fritilia, okay? Blanket flower. Okay, so now show us what it looks like on the GPU. So Ryan, this is now running on NVIDIA GPUs. Okay, so this is Volta, right?
Yep.
This is what? Hey guys, yeah, that's right. The more you buy, the more you save. Okay, check this out, Ryan. So this is one GPU.
One GPU.
This is one GPU.
Exact same network.
This is one GPU.
Yep.
That's nuts. This is one GPU. How are we going to make it a living if this is one GPU? So this is one GPU. Okay, and so suppose, okay, well, let's Kubernetes this thing.
Yep, we got it running in Kubernetes. So imagine like our app gets so popular, everyone wants to know about flowers, and we get a larger load. So we're going to scale this up. Let's look at what a larger load looks like. So there we go. That's a larger load, so we need to handle that load. So what we do is we can ask Kubernetes to say, hey, let's make multiple replicas of that same container. And so I'm going to add 8 replicas in. You're going to see them come in. And I'm going to add them into the load balancer. And as I add them in, you're going to see it just get faster.
Wow.
That.
Guys, this is like magic. Kubernetes is orchestrating this data center. And what's amazing is this. So Kubernetes assigns this pod, which is basically a service or an application that contains a whole lot of containers. Okay? It could assign this pod on one GPU, on many GPUs in one server, on many GPUs and many servers. It can also assign it across data centers. So you could have some of it in the cloud and some of it in data center. You could have some of it in this cloud, some of it in that cloud. Truly amazing. And all of this stuff is happening completely invisibly because we've made Kubernetes GPU aware, and because the NVIDIA architecture and all those containers are literally everywhere. And so as a result, this magic could happen because the foundation we've been layering and we've been growing now for several years is now come together. And this moment, the Kubernetes moment, pulled it all together. Ryan, what else you got for us?
So as you said, not only can we run it in our local on-prem data center, but we can scale and we can burst into the cloud. So let's take a look at that right now. So I'm going to
Saturn V is at the Nvidia, our Nvidia data center. It's our supercomputer. There are 660 DGXs in Saturn V today. So 660 petaflops. It's about to get upgraded, as you can imagine.
It's going to get exciting. So I'm going to add 4 more from the cloud. So this is going to be an example of cloud bursting or cloud fallover. So here we've turned on 4 in the cloud. They're active. And what I'm going to do now is show you self-healing. So I'm going to kill off 4 of these GPUs that are running right now on Saturn V. And what you're going to see, and you're going to have to watch really closely, is we're going to take a bit of a performance hit. And then those AWS GPUs are going to jump right in, and the performance is going to come back up. Ready? There they go down. And you didn't even see it this time. Sometimes it's that fast.
Wow, that's an incredibly good demo. Ladies and gentlemen, this is a demo of resilience. A demo of resilience where before and after is exactly the same. I bet you really enjoyed that. We don't have to show it again because guess what, guys? It looks exactly the same. Okay? A demonstration of resilience. And this is one of the most amazing things about modern hyperscale computing. And we now have cloud to cloud. We have any cloud. We have cloud to prem. We have any prem. And so the NVIDIA architecture, all of these frameworks, all GPU accelerated, is now possible, orchestrated under Kubernetes so that it can basically run everywhere. Ladies and gentlemen, Ryan. So, the NVIDIA Kubernetes on NVIDIA GPUs. Kubernetes on NVIDIA GPUs. Super exciting about that. The inference movement on our GPUs is really moving fast. We now have up to 40,000 downloads, I think, of TRT, and it's just picking up steam. And the reason for that is because all these different companies are developing their networks and models, and it's time to deploy them. And they want to deploy them into servers. They want to deploy them into PCs, WinML. You want to deploy them at the edge, IoT devices on NVIDIA Jetsons. You want to deploy them on supercomputers. You want to deploy them on hyperscale. You want to deploy them inside companies with SAP. The number of ways you could deploy software is, of course, quite large. And now, with all of our new battery of accelerations for inference and Kubernetes on NVIDIA GPUs, we can now literally blanket the world with this new approach. So super excited to do that. Ladies and gentlemen, the NVIDIA AI inference. So this is the NVIDIA AI platform. Today we announced that the GPU Volta has been doubled in memory size to 32 gig. It's now available in DGXs and available in the cloud soon. NGC is now on AWS, GCP, AliCloud, and Oracle, and more are being certified. We're certifying them as fast as we can. The NVIDIA GPU Cloud now has 30 optimized GPU containers, and this year we announced 4 new battery of acceleration capabilities for inference. New TensorRT 4.0 that is able to handle RNNs and sequence-to-sequence type of models, TensorFlow deep integration, Caldi acceleration, which is the most popular speech recognition system, Onyx, an industry standard backend for inference, and WinML optimization into that. And sorry to say, Titan V is still out of stock. Apparently, the popularity of Titan V is quite high. And so we'll make them as fast as we can, and we'll put them back in the store. And if you could just be patient. Lots of Titan Vs being sold. The NVIDIA AI platform. You know, all of this, one of the things that, as I was reflecting on this keynote, one of the things that just gives me so much pride, and it's such a great creation, is NVIDIA research. For 10 years, Bill Dally has been building NVIDIA research. Bill Dally is my chief scientist, and he's the head of NVIDIA research. And it's 200 people strong, but the productivity of this organization is just utterly incredible. They're doing fundamental and basic research across the entire stack of computing. You know, the number of fundamental basic research, computer science, industrial computer science organizations, research organizations that are working across the entire stack, all the way from circuits to networks, to parallel processor architectures, programming models, all the way to computer graphics and deep learning. Those aren't that many. And this is 200 people strong across the world. And the thing that's really special about the way we do NVIDIA research, it's really a hub and spoke system. They're collaborating and doing research with all of the product research teams. We have hundreds of researchers around the company, all working together to advance the future of computing. Some of their contributions you have already seen. NVIDIA research initially started RTX, and the 10 years worth of work that they've done has resulted in the NVIDIA RTX, or NVIDIA Optics and NVIDIA RTX technology. NVIDIA Switch that was described today that made the world's largest GPU. cuDNN, the library that has now revolutionized deep learning, all originated at NVIDIA research. I'm so proud of these guys. And you guys have seen some of the really amazing work. Progressive GAN that was recently described that caught a lot of attention because of the amazingly realistic faces that it's able to generate. And this is one of my favorite technologies, noise-to-noise denoising. Noise-to-noise denoising. That's one too many times you said noise. But that's got to be incredibly good technology. I showed it to you earlier today. It's basically super rays. So wherever these black dots are, ray tracing hasn't completed yet, but somehow using artificial intelligence, we're able to predict what color and what light it should have been and put that up on the screen in advance, finishing the frame much, much faster. Okay, so let me show you one thing here. This is, what you're about to see here is this. Imagine we taught a network how to draw. But we wanted to teach this network how to draw photorealistic images. And so what you're looking at here is, of course, a road. You can imagine that as a road, just like that. Based on our intelligence and based on all of our experience, we know that that's a road. The pink, what is that color? Is that purple? Fuchsia? That's fuchsia? Okay, fuchsia is roads. Blue is cars. Posts are yellow. Green is obviously trees, and gray, that's got to be buildings. And we take this image, and we put it into the artificial intelligence network, and we say to it, produce a photorealistic image. And this is what it did. Okay, we trained this network to do this, and now it's going to create photorealistic images. All from this. What do you guys think? Is that just amazing? So this artificial intelligence network is actually synthesizing information, and we're teaching it to synthesize roads, things that you would see on roads, and synthesize it in a photorealistic way. Ladies and gentlemen, NVIDIA research is now all over the world. I'm so proud of this team. Here's Seattle, Redmond, Santa Clara, of course, Salt Lake City, Austin, St. Louis, Westford, Virginia, Charlottesville, Durham, North Carolina, Helsinki, Lund, Berlin. Some of the greatest cities around the world, 200 people strong. We're growing. Reach out to us. We love to work with you. The transportation industry is the largest industry, one of the largest industries in the world, $10 trillion large. And we believe that someday everything that moves will be autonomous or have autonomous capabilities. As you guys know, there are several very important dynamics that are happening to the transportation industry. One, first of all, the cities are getting too crowded and people are having to move further and further away. The online purchasing phenomenon, the Amazon phenomenon, is causing more and more people to not go to the store, but to wait for the store to come to us. Somebody has to drive those atoms to us. And as a result of so much increase in population, another billion people are going to come into society in the next 12 years. We already have over 1 billion parking spaces. We have 2 or 3 billion parking spaces waiting for us right now as we speak in anticipation of us needing it. And it's being built in the most precious places in the world, city centers. Autonomous vehicles has the opportunity to reduce the cost of transportation, make it easier for people to get around, live further away from the cities and work, and of course, revolutionize the way we design cities. However, it's hard. Safety is the single most important thing. It is really, really hard technology. It's probably the hardest computing problem that the world has ever encountered. Safety is the most important thing. And as we're reminded just last week with the fatal accident that happened, we're reminded that this work is ultimately vitally important, that we have to dedicate ourselves, commit ourselves to solving this problem. But we have to solve it step by step by step with just incredible amounts of capability because we know so much is at stake and we have the opportunity to save so many lives in the future if we do it right. And so we at NVIDIA, we're dedicating ourselves to this problem, the grandest of computer problems. Just imagine this. You've got these cars with all these different sensors. Some have a radar that could sense motion, LiDAR that can measure depth but don't see very well in light and snow and fog, cameras with super high resolution but can't see in the dark, infrared that can see in the dark but doesn't have very high resolution. We take all of these sensors and we fuse them together into a super sensor. This sensor, this super sensor, we call them sensor fusion, this super sensor could measure depth, it could recognize motion, it could detect things, it can understand the scene, it could see in the dark. But in order to do this and to compute it in such a high rate of speed as the car is moving and to take action so quickly is incredibly hard. The algorithms, this entire system has never been created in totality, not even once. This system has not even been once created in totality. We're dedicating ourselves to solving this problem. This is the ultimate high-performance computing problem. This is the ultimate deep learning problem. This is the ultimate AI problem, and we think we can solve this. We think we can make just an enormous contribution to this. And so it's a hard problem. The software is hard. The algorithms are hard. But it's also a safety problem, meaning these computers have to continue to operate well even when faults are detected. We have to be able to detect the faults when it happens, and we have to manage the faults, meaning continue to manage the car properly and safely even after we've detected the fault. The level of functional safety required to make this thing happen is just really, really high, a level that the computer industry has really not dedicated itself to understand, because this is something in the transportation industry, is something that is obviously very well understood in the airplane industry. We've dedicated our last 5 to 7 years to understand this entire system. And what NVIDIA is dedicating ourselves to do is to solve the problem from end to end. There are 4 basic pillars to what we do. There's collecting of data. These cars are collecting petabytes and petabytes of data. We take these data and we have, well, collecting of data. I'm going to come back to that. Training models. These models, of course, cars, road signs, people, bikes, trains, motorcycles, trees, hydrants, you name it. Roads, potholes, lanes, curbs. Things are all over the world. The world's very diverse. We have to train our neural network with extreme precision to do this. And then we have to simulate it. Simulation is going to be the foundation of success, and I'm going to talk about that in a second. And then lastly, drive it. Creating the driving computer, that's the computer that has the horsepower to compute everything in real time, energy efficient, like all of the energy efficiency comments that and examples that I've shown you. Because ultimately, energy efficiency translates to battery life, and battery life translates to mileage, miles of operation, which for many car companies translates directly to their earnings. And so battery life matters. Battery life also allows us to put multiple redundant computers inside the system. The more energy efficient we are, the more computing systems we can put inside the car so that it could be redundant, diverse, and provide functional safety. We have to drive the car, the computer, the system software, and all the algorithms on top. We're building the end-to-end systems. First, let me talk to you about perception. In fact, you can almost piece together all of the work that I've talked about so far into this system. It's called the Nvidia Perception Infrastructure. We are building a supercomputing infrastructure in our company. There's 660 petaflops of supercomputing horsepower already in our company. This is a giant data problem. I've already just said each one of these cars are collecting petabytes and petabytes of data every single week. And from that data, we label it in our data factory. We use all kinds of tools and AI tools and trained professionals to label each and every one of these images so carefully. And the reason for that is this. We label it once, and cars in the millions get to benefit it forever. And so we take labeling incredibly seriously. This is not a crowdsourcing problem. This is a professional labeling problem. We have 1,500 people. We're labeling about 1 million images per month. And we're just going to keep on labeling. And from these labels, we're able to create the perception networks that you'll see of incredible levels. We train them on our DGXs that I've just mentioned. It's not just a supercomputing problem, it's a software infrastructure problem. In the future, in the past, your source code is your code. In the future, your source code is your data and all the code and all the training methodologies and recipes that you applied in order to create that model, because you want to be able to trace it, you want to be able to repeat it. This infrastructure inside NVIDIA is called the perception infrastructure. It's a massive investment, and it's just something that I'm so proud of. At the end of it, it produces networks. We already have 10 networks inside our car. The self-driving car is not one network. It's a whole bunch of networks, and there'll be a whole bunch more. We already have 10. By the time that we ship in a couple of years, call it 20 or 30. Each one of the 10 networks, there are 10 DGXs assigned to one network, and they could produce experiments every single day. And then we have to validate it and verify it. Many of those DGXs will then have to be used for testing and verification against the entire body of work and the test data that we've stored up over time. Let me show you some of the results. And so, guys, let's go ahead and play it. And so here's a whole bunch of different networks that we've created. This is perception network. You're seeing car detectors and the bounding boxes. You're going to see lanes. Not only do we detect things that we shouldn't collide with, we also have to detect spaces so that that is safe to drive to. Meaning, on the one hand, we detect obstacles. On the other hand, we detect free space. So between those two algorithms, we have redundancy and diversity. We have so much redundancy and diversity all through our system. We do everything 2 or 3 different ways and 2 or 3 different times so that we can make sure that what we ultimately do is right. Distance perception. Here's using an artificial intelligent network that was trained with LiDAR labeling so that it could predict the distance of objects. Weather. We've trained it with so much data that is now robust across all kinds of poor weather conditions. We use cameras for object detection. We use radars for object detection. We also use LiDARs for object detection. Not just how far away they are, but based on the pattern of dots that are coming back our way. The resolution of LiDAR is not as high as camera, but the depth information is really good. Based on the point cloud that comes back, we do point cloud processing on CUDA, which is incredibly good. We do ICP processing, iterative closest point processing, for registration, and then we use deep learning to detect what those objects are. And so LiDAR perception. We do scene perception. One of the hardest things isn't just to detect a light. Intersections where you're supposed to stop or be cautious aren't always properly labeled. And so we have the ability to detect scenes of all kinds of intersections so that we could be much, much more alert. Our path perception is not just about calculating the path, but calculating perceiving the trajectory of the path that is most comfortable and safe. LiDAR localization. You got to figure out exactly where you are in space compared to an HD map. You want to figure out where you are relatively in space using your camera as well. Camera localization, even to HD maps. So if you had an HD map, we could figure out where we are. It's an additional sensor, in fact. And then lastly, every single car is also a mapping car. If you have all of this technology inside your car that I just mentioned, your car becomes a mapping car, which means that when you drive it in the beginning, every time you drive it, you're mapping your space. And so as you know, 99% of the time, we're driving the same route. And most of those routes won't have an HD map in the beginning. And so we'll use our own cars, your car, to map and create a really high-fidelity, three-dimensional map. And then after that, you could use it as an extra sensor to give you additional information to localize within it for safety. Okay? So camera-based mapping. Why don't we show them? What we've done is, every time we're together, I show you a homemade video. And this homemade video are some of the latest clips, if you will, the latest clips of some of our recent achievements. We're making progress all the time. We are far from finished. There are several thousand engineers right now working on autonomous vehicles. We're going to work on this for another 2 or 3 years before we ship in volume cars. In the meantime, of course, we're going to develop and offer development systems and training systems, simulation systems of all kinds. But this is going to be a long journey that is step by step by step. As I mentioned, this is really one of the most complex computing problems we've ever encountered because of the diversity of the problem, the complexity of problems, all the different types of algorithms involved, and multiplied exponentially as a result of safety concerns. And so let me just show you some of the latest clips. Guys? Wow. God, I love you guys. It's amazing how much, as I'm watching this, it's just, all of the software and all the technology that has been created to make all of this stuff happen, it's just, it's washing over me. And it's truly an amazing thing. And the reason why it's so hard, the question is, why don't we just put up a car, and demo a car? Well, it turns out our challenge is we're trying to create a AV computing system and an AV driving flow and infrastructure so that the entire transportation industry can take advantage of this massive investment that we're making and create the future of autonomous vehicles. And as you know, there are all kinds of different sizes and shapes and price points of cars. But every one of them should have the advantages of autonomous capability to either help you drive or keep you safe while you drive. Notice we showed you earlier Janine, it was a video of Janine, and she's driving. She's pretending like she's sleepy. She's never sleepy. I've never seen her sleepy once. She's pretending like she's sleepy, and our AI inside the car is monitoring her, making sure that she's looking in the right direction, that her gaze is still active, that somehow she doesn't appear sleepy, making sure that everything in the cabin is safe and nobody's doing crazy stuff. And so using driver monitoring and cabin monitoring and AI, we're able to make sure that not only is the car doing the right thing, but the passengers inside are doing the right things. This entire infrastructure, this entire system is just such a great undertaking. And we're doing this in a way that is mindful of the fact that we're not trying to build a chip, we're not trying to build a AV system. That in the end, this is an AV computer. And as you know, computers are software defined. One of the most powerful things about today's cloud computing is that the entire cloud infrastructure is software defined. One of the most amazing things about today's cell phones versus yesterday's feature phone is that today's cell phones are software defined. One of the reasons why the PC has become such a revolution instead of a typewriter is because the PC is software defined. Architecture matters. If you're a software engineer, you care about the hardware architecture. And because NVIDIA is not a chip company, we are a computer architecture company. We're a software company. We care about computer architecture. We care about the fact that the software will run on all of these different computers for as long as we shall live, so that we can make the software better and better and better over time, and the entire installed base of fleets and cars that we've deployed gets better and better and better and safer and more comfortable over time. And so we created one architecture roadmap, and it basically starts like this. 2 years ago, we introduced Drive PX Parker, and we created, that's a one-chip solution for a very basic car, and then we created a 4-chip solution for Drive PX2, which is the development system for most of the autonomous vehicles that you see around the world. Drive PX2 at the time, when I brought it out, we were laughed at. People laughed at me for bringing out such a large computer. Well, it turns out I did make a mistake. I didn't make that computer large enough. And the reason for that is because the amount of software that the world needed to develop is far more than what anybody realized. And so our basic methodology is this. Then 2 years later, this year, we created the Drive Xavier. Basically, we took 4 chips, the computational capability of those 4 chips in those 300 watts, and we shrunk it into one miracle chip. Xavier is the most complex SoC the world's ever created. It's great for high-performance computing, it's great for deep learning, it's great for computer vision, sensor fusion. It is the largest single chip we have ever made short of Volta. 9 billion transistors. Unbelievable amount of engineers worked on it. Xavier is now sampling. Then from Xavier, we created a 4-chip system. 2 Xaviers and 2 Voltas together. Another running at a very low temperature and voltage, another 300-watt computer emerged. And that 300-watt computer is being used in robot taxi and self-driving car system development all over the world. We're sampling both of them today. Both of them will be in production by the end of this year. Completely architectural compatible, auto grade to the extreme temperatures and operating conditions of a car. It is super energy efficient because battery life matters, redundancy matters, and it is also ASIL D. This is the first lineup of computers that NVIDIA has ever made that stands up to the highest standard of functional safety. ISO 26262, ASIL D is a rigor like you have never seen before. From process, because ASIL-D has only been done on small computers, not computers of this type, and not on a software stack of this complexity. This is just a gigantic investment on our part, but it's so important, and we've got to do this right. All of the engineers that are working on this, I want to thank you so much for doing this. Everything from the architecture to the design, the resilience, the redundancy, the diversity, even the documentation, so that it can ultimately be certified and traced all the way back if anything were to happen. Because 100% of all the IP and all of those chips were created here at NVIDIA. We have the ability to produce traceability for as long as we shall live. This is just a gigantic investment, and we take it so seriously. But we're not stopping here. Drive Pegasus, as powerful as it is, multiple of them are being used in self-driving cars, driverless cars. And the reason for that is because there's so many LiDARs, so many cameras, so many radars that are being deployed. So we're not stopping here. Our next generation is called Orin, and we're going to take basically those 8 chips, two Drive Pegasuses, and we're going to put it into a couple of Orins. Incredible amounts of computation in one little chip. And of course, with Orin, there will be discrete GPUs that we will continue to build. There are some code names I won't share with you today. I'll save some surprises for next time. It will create also an amazing processor for autonomous driving cars. Auto-grade, super energy efficient, fully ASIL-D, huge investment. NVIDIA's Drive roadmap. Let me tell you why this problem is just so incredibly hard. Well, it turns out the world, civilization drives about 10 trillion miles per year. Okay, 10 trillion miles. Just you got to get that number in your head. It's 10 trillion miles. It's 1,000 billion. It was 10,000 billions. 10 trillion miles. 10 trillion miles. And in the United States, 770 accidents happen from 1 billion miles. 770 accidents happen from 1 billion miles. The safety work that has been done throughout the years in the United States has really reduced the amount of fatalities and accidents. And yet, it would take you driving 1 billion miles, society driving 1 billion miles in the United States to produce 770 accidents. And so the question that you have to ask yourself is, how confident are you when your fleet of test cars of 20 over 1 year has driven about 1 million miles? It takes 20 cars driving test drive all year long to test drive 1 million miles. And yet it takes 1 billion miles to have experienced 770 accidents. And we're trying to build a system that is better than humans at driving. And so clearly the amount of coverage, scenario coverage and miles coverage is just not possible in real life. And this is where NVIDIA's skill can really shine. We know how to build virtual reality worlds. And so we imagine this, that in the future, there'll be thousands of these virtual reality worlds with thousands of different scenarios running at the same time. And our AI car is navigating itself and driving and testing itself in all of these virtual reality worlds. And if any of those tests were to fail, it would send us an email. We would jump into it in virtual reality and figure out what's going on. You guys see that? So we have all these virtual reality worlds. Well, let me show it to you today. Mark? So what we're going to show you is this. This is a virtual reality simulator. And before you start, this is the front view, your side mirrors, and your rear view mirror. Okay? Go ahead, Mark. Hey, Mark, how's it going?
Hey, good, Jensen.
One of NVIDIA's veterans.
Thank you. Well, let's start this thing. We're generating our world. We're running 4 simultaneous cameras, as you mentioned. We've got a pretty aggressive driver here in front of us. We've defined a scenario that's causing all the traffic to jam up. But as you mentioned, we got all the cameras. We're running on multiple GPUs, so it's a scalable system. As cars get more and more sensors, more cameras, more LiDARs, we're going to need the horsepower of multiple GPUs. And we're showing that to you right here.
Okay, so we could do, of course, we could simulate daylight scenario. Let's simulate other scenarios.
Okay, let's, why don't we turn the lights out and go to night. So here's the same setup, only now we're doing all the dynamic lighting. So the headlights of the cars, the light posts that are lighting the road, the lights under the bridge as we drive under here, these are all dynamic real-time lights.
And the key here is that the fidelity of the simulation has to be sufficiently high that the sensor stack, all the software that we create, would just operate as they would in real life.
That's exactly right.
Right? So and every one of the sensors needs to have GPU associated with it to generate its view of the universe, its view of the world that it's in. And so today we're simulating with 4 GPUs, with 4 cameras, but obviously we have the ability to spawn off a whole large number of GPUs. So if you have 8 LiDAR systems around your car, you have 8 cameras around your car, you have 6 radars, we have the ability to generate all of that and feed that information into our sensors. And if we are successful in doing that, our artificial intelligence network, all the software that we ran, that we developed, should just work. So Mark, let's turn that on.
That's right. Okay, so let's, here we go. Now this is what our drive stack is seeing on Drive PX. This is all the detection of the cars in the world, the lane detection you're seeing going on, and we've been self-driving this whole time, by the way. So as we ran into that little traffic jam, the Drive PX detected it and slowed down and kept us safe.
And notice we're detecting all the cars, we're detecting all the lanes, but here's the amazing thing. Earlier, the video that you saw were real cars in the real world. We didn't change one line of code iota. The code is exactly the same code that was developed by the engineers. We, of course, copied it over send it over to this data center, and it's running on exactly the same Drive PX, Drive Xavier, and Drive Pegasus computer that we would drive in the car. And as a result, it's exactly the same sensor response. And the perception, the localization, the planning stack all work exactly the same way. And now you're at the end of your...
So we reached the end of that scenario. Can I show you another one?
Yeah, show me another scenario.
So let's switch to the other system.
And so this is one of the beautiful things in virtual reality. We could create whatever scenario we want. And as you know, in test car driving, you could go days, months, weeks, and never run into a weird scenario.
So there's...
And so we could create all kinds of strange and corner conditions in virtual reality. Go ahead, Mark.
Sorry. So the same adversarial driver just came through. And now we found one of San Jose's finest is in pursuit of him.
You see the cop coming up on the back, the policeman coming up on the back, and it's coming up on the side. There you go.
So we come in, and of course all the dynamic lighting, so you're seeing the red and the blue lights light up the world. Some of that strobing effect could affect the sensor, so we need to make sure we're modeling that correctly.
That's really terrific. And so, the first is to recreate virtual reality in all kinds of weather conditions and day and night conditions. It has to have the fidelity and the performance that basically simulates reality. 2, that simulation of reality has to be so high, and the computer itself has to be able to run the original unchanged software so that we could test everything as is inside a virtual reality world. And when it passes that, then we can take it and put it into the car completely unchanged. We just OTA it directly into the car, and it should just work. And then 3rd, we could use it to create extreme, corner, rare scenarios, and it's completely repeatable. Every single time that police car shows up exactly the same way.
That's right.
And so we could have the ability, if with repeatability, engineers could debug systems.
That's right.
These 3 fundamental capabilities are made possible. We call this Drive Sim.
That's right.
Ladies and gentlemen, Mark Daly. And so Drive Sim, just imagine the amount of technology that has been brought to bear. Drive Sim, the simulator, but most importantly, the computer inside it and all the driving stacks. And so you got the image generator. This image generator is generating the world. Now, this image generator, in the context of a video game, this image generator is a gaming PC, and the person that would be driving the car would be a person driving the racing simulator. But no, we replace that person with a artificial intelligence AV computer, a self-driving car computer. Inside the self-driving car computer is the drive Xavier and the drive Pegasus. And they're connected. Literally, the output of the image generators go into, and there's a sensor adapter, and it goes directly into the drive computers. The exact same software stack runs, and it performs the right actions, perceives the world, performs the right actions, sends back the driving control to the image generator, which controls this virtual reality world. We will have thousands of, we call this drive constellation. Pegasus in the sky, a constellation of them. Pegasus in the sky, a constellation of them. We're going to have thousands of constellations. These virtual reality worlds will all be running simultaneously, and hopefully we could cover a large coverage of scenarios. With just 10,000 constellations, we can cover 3 billion miles a year. Incredible. So ladies and gentlemen, this is the Nvidia Drive Sim and our constellation, and it is how we're going to bridge the gap between actual test driving and the trillions of miles and the billions of miles that we need to experience over time. Well, as I mentioned, NVIDIA has created a platform. It's an open platform, and it takes a community to build the future of autonomous driving. It's about the car companies, it's about the trucking companies, it's about mobility service companies. It's about the tier 1 suppliers that are expert in building these systems and components for car companies. But it's about mapping companies, it's about sensor companies. We work so closely with all the LiDAR companies and all the camera companies to make sure that these future sensors are as high fidelity, as high performance, and as robust as possible, and that the algorithms they use are as efficient as possible. We work with startups all over the world. NVIDIA's platform is an open platform. Last year, we had 320 partners. The year before that, we had 250 partners, and today we have 370 partners. We're working with people all over the world. This is one of the world's largest industries. We're making the fundamental investment for the future of AV computing. The AV computer, all the software driving stack, and the end-to-end development system that will support this fleet and this industry for as long as we shall live, and continue to make it better over time, taking it step by step as we are so mindful of safety. Well, the self-driving car is the first. In the future, robots will augment and will assist us in all kinds of different places. One of the areas that we already talked about is, of course, the Amazon effect. We used to drive to pick up groceries. In the future, groceries will come to us. And this is going to happen in all kinds of different industries. Artificial intelligence and autonomous machines will help revolutionize just about every single industry, making us more productive, making us more efficient, do things that are otherwise impossible to do or too laborious to do or just simply too hard to do. And so we've created a platform like we've done with Drive. We call this Isaac. Today, we're going to release the first little version of that. This is such a great achievement. And so basically, in the future, you're going to be doing simulation as a development system because these robots have to work in a three-dimensional world. And so we created a three-dimensional world simulator we called the Isaac Lab. In the Isaac Lab, we will develop the perception capability, the localization capability, the mapping capability, and the planning capability that is necessary for robots and autonomous machines to navigate these complex worlds. And so we already have our deep learning systems that I've mentioned. And then we take, because it's hardware in the loop, the hardware is driving the simulator. When you're done with the simulator, that hardware should be able to run the entire software stack, and we call that the Isaac SDK. The Isaac SDK running on top of our little computer we call Jetson, we can deploy that. We made a quick little video for you. All you have to do is come to this website, and we'll take let us know if you're interested, and we'll get you going on an Isaac SDK. So, ladies and gentlemen, this is the Isaac robotics platform ready to come to the world. Ladies and gentlemen, Isaac, our new platform, the future of robotics. This is a development system, lots of software developed for it, and of course a simulator that goes along with it, and this little tiny computer we call Jetson. It's been put together for you to start developing the future of autonomous machines. Look, I have one thing that I want to share with you. This is something we've been working on, and it's just so exciting. Now, it's never been seen in the world before, and it's far from finished. It's far from finished, and I thought that as a close, I would invite you into NVIDIA's lab. NVIDIA does a lot of things in the holodeck today. We create the future in virtual reality because that's the only place you could create it, and we created this thing called holodeck, as you guys know. And this project is really about thinking through the entire path of how to deploy these self-driving cars into the world. And as you know, when you have a car that is driving by itself in autopilot mode, the driver is the backup system. The driver is the backup system. If you have a driverless car, who is the backup system? And so the backup system likely will be another person. We would like humans to always be the backup system of AI. And so the question is, how do we solve this problem where an autonomous machine has no operator? It could be a little tiny robot like Carter that you saw earlier. It could be a delivery vehicle. It could be a little agriculture, little farming equipment, a little Caterpillar tractor that's roaming around doing things. And there are no operators. And so the question is, how do we create the backup system if something were to happen that we have to go and, if you will, get it out of harm's way? Okay, and so we imagine this. We know that virtual reality has the ability to teleport us. Virtual reality has the ability to teleport us into a new world, into a different world. And so before I'm going to show you a little something. This is Justin Ebert, please. Justin Ebert. Justin is going to help me with this demo. We are currently in the holodeck. I'm going to explain a little bit more as we go through. Okay, but imagine there's a car in the world somewhere, and we need to help it. And so the question is, how do we do that?
Thanks, Jetson. Let's check it out.
So we're in holodeck. We just created a virtual reality car.
We call this Drive Lab, and this is where we have a virtual car where we can take over. Our operator, Tim, here is sitting on the side stage, and we can see sensors coming in from the vehicle, the remote vehicle that needs help.
And don't go anywhere, just, hey.
Oh, we're not going anywhere.
Yeah, okay.
Yeah,
all right.
Yeah, we're not going anywhere. We're going to wait and talk this through. So you can see there's
This is so incredible, you guys. This is just utterly incredible.
Yeah.
First of all, I'm going to hand it back to you in just a second.
Yeah, no problem.
What you're looking at is live.
Yeah.
This is holodeck. This is holodeck. There's a virtual reality car.
Yep.
Okay? The virtual reality driver is sitting right there. His name is Tim Wong. Tim, if you guys raise your hand. There you go. Tim is the virtual reality driver. He is inside this virtual reality car. He is inside the holodeck. He's not with us. That's just a sack of humanity we call Tim Wong. Okay? And so Tim is currently in holodeck. He is looking at this virtual world, and you see the video that's being piped in? That is literally live. That is live right now. Okay? All right, Justin, take it away.
Yeah, no problem. So yeah, as Jetson said, this is actually out back here and in a private area. And let's bring in Tim. So we can show him taking over inside this vehicle here, and let's show that he has control over the car as well. So there's the real car out there. And so Tim, you can turn the steering wheel a little bit. We can see that we've got.
Oh, come on, cut it out.
Come on, that's fun. Yeah, so he engaged.
Are you guys putting this in your head right now? There's Tim in reality, but he's inside virtual reality, controlling a car that's in reality, but it's not here. Are you guys following me? Okay. It's like 3 layers of inception right now. The mind clearly exploded.
We've engaged remote drive, you can see, so he knows he has control.
I still remember when we were talking about this, creating this, the people that were explaining to, we got to build this thing. I was like, okay, explain to me one more time.
Yeah, you can't understand until you see it. Then it all makes sense. Okay, so I think we've seen this. Let's take a look from Tim's perspective for a second here, and we can have him take off and actually drive the car. As you can see, he's blocked. There's a vehicle here that's doing some unloading, and Tim, look down just a little bit so we can see your perspective, and he can now operate this vehicle around this obstacle and maybe take it to a safe spot in a parking lot for us. And hopefully all. So we're doing this really slowly and safely in a cordoned off area here, and he's going to try to turn off into the parking lot. Now you can see a little bit on the left here. Tim's view is
Tim is in there, guys. There's Tim right there, the invisible man.
And Tim's view is very broad. He can see all 3 screens and get a full perspective of everything that's going on in the car. In the future, we can represent all kinds of LiDAR systems and everything, slowly. So, yeah, maybe we could take a look there.
Look at him.
Yeah.
There he goes. Go, Tim.
There's the team racing after the car there. And let's see if we
you know, look, what Tim is experiencing right now, he's sitting inside the car, and he feels like he's inside the car, and he feels the car around him. And that's why he's able to, look at that, he parked in a parking space.
Nice job, Tim.
Hey, guys, thank you. Thank you. You guys are amazing. Thanks, guys. Ladies and gentlemen, what do we call this? I have no idea. Yeah, that's right. We call this amazing. So, guys, I'm so proud of you. This is such incredible work, and this is such important work. And as we know, one of the amazing capabilities of the future of autonomous machines is we can go somewhere that we otherwise can't. We could be fixing something. The robot could be fixing something, rescuing someone, and now we could literally, through VR, teleport ourselves into the mind of the autonomous machine and be there. Does that make sense? Teleportation. And VR is our way of doing that. VR augmented with autonomous machines is our way of doing that. Teleportation. The future has arrived. Pretty exciting. Thanks a lot, guys. I'm so proud of you. Okay, we've covered a lot of stuff today. We talked about a brand new, a revolutionary computer graphics technology we call RTX, our dream come true. After all of these years, from architecture to algorithm to AI to integration into all of the APIs in the world and the tools around the world, we have introduced real-time ray tracing to the world finally. We call it Nvidia RTX, and it will run on a revolutionary workstation called the Quadro GV100 with 32 gigabytes. We also announced our brand new Nvidia AI platform, all of the new updates from the largest GPU in the world, $1.5 million of value, all for my friends for $399,000. And Nvidia's DGX2, 2 petaflops of computing, incredible amounts of memory, 512 gigabytes of HBM2. TensorRT and integration, deep integration into TensorFlow and Caldi has expanded our ability to reach the hyperscale workflows around the world. In aggregate, speeding it up by 100x, which allows us to enable people to buy more GPUs and save more money. And not only that, we made it easy to deploy. Kubernetes is now on NVIDIA GPUs. Kubernetes on NVIDIA GPUs. Just really, really exciting. And don't forget, what makes TensorRT such an incredible achievement and what inference is so hard is because of one word. You guys know that word? Plaster, that's right. And so, what a great audience. What a great audience. And then lastly, in our driving stack, we introduced our one architecture. We'll be in production by the end of this year with our first full ASIL D, full driving computer called Xavier and Pegasus, and the next generation called Orin. But one of the most important things we can imagine doing is to create a simulation environment so that the automotive industry can cover the gap between 1 million cars, 1 million miles, and 1 trillion miles. That level of that many orders of magnitudes of difference in coverage has to be covered in some clever way, and we call that Drive Sim. Running on our server, we call Drive Constellation. And we introduced 2 new platforms, and I'm going to talk about more and more and more every single year so that we can engage these new industries. One of them is Isaac, our robotics platform, and Clara, our medical imaging supercomputing platform. Ladies and gentlemen, it's great having all of you here. Thanks for your support, and have a great GTC.